Hello, fellow chemists. Jolly here. Today we are going to be talking about electronegativity. Now, the first question is, what is electronegativity? And that is based on how much an atom wants electrons. So electronegativity is how much it wants electrons, or another way is how hard it is pulling electrons towards itself. Okay, so basically it is wanting electrons. Now, where does that come from? Just a really quick review, something called effective nuclear charge, ZEF. Oh no! I never wanted to hear that word again. It's so useful. And let's just do a real brief review of effective nuclear charge. All right, basically effective nuclear charge means how effective the protons are actually pulling. And there's two considerations for this. One is distance, and the other one is the number of protons, and if you will, the number of electrons. Okay, so for instance, let's take a look at hydrogen. So hydrogen has one proton in its nucleus, and it has one electron out here. So this electron is seeing or feeling the entire pull of the nucleus. So that is not bad. Okay, so this is an n equals 1. That's that first shell. Well, helium has two protons in its nucleus, and it is pulling on, wow, those are so not circular, but that's okay. It has two protons in its nucleus, and it's pulling on two, but if you'll notice, it's the same distance away, but this one has two protons pulling, and this one only has one, so it has the higher effective nuclear charge because it has the most protons at the smallest distance. In fact, helium, who is not right here, is the element that has the highest effective nuclear charge on the entire periodic table. Well, wouldn't that make francium the least? And the answer is yes. The answer is yes. It's as far away with the fewest amount of protons possible. All right, well, that's what happens on the horizontal row. Okay, so the effective nuclear charge increases this way. Well, let's look if we go down. So let's take a look at hydrogen versus fluorine. Hydrogen versus fluorine. So here's my hydrogen. So my fluorine has 9. Guess I should write that, huh? Hydrogen, helium, fluorine. And then it has in the n equals 1, but we're also out into the n equals 2. So there are 2 in the n equals 1, and then there's 7 hanging out here. 1, 2, 3, 4, 5, 6, and 7. And what I'm drawing here is, remember, called the Bohr model of the atom. Now, let's take a look. I love that there are 9 protons in that nucleus. Oh, I love it. And so these two, yes, they are feeling that 9 proton pull. But out here, I have increased the distance, but I also run into the problem of, do you see these two right here? I've drawn them so that they're interfering. So this inner one, the red one, is actually in the way of the blue one's view to the nucleus, and that is called shielding. And so that is a problem. So fluorine has a less, okay, it has a less effective nuclear charge than, say, helium did with just the two. So we just need to decide, what about hydrogen versus fluorine? Hydrogen versus fluorine. Now, the reason I pointed this one out is because fluorine is the most electronegative element on the entire periodic table. it has the greatest effective nuclear charge to hold on or pull electrons towards itself. Now, hydrogen would love to. I mean, hydrogen can pull one towards itself, but it just doesn't have that oomph that the fluorine has. So fluorine is the most electronegative element on the entire periodic table. Now, you all noticed that I'm missing an entire column. Okay, where are my noble gases? We could talk about effective nuclear charge and noble gases, but when we're dealing with electronegativity, electronegativity is wants electrons, or how hard it's pulling electrons towards itself. The noble gases don't want any. They have a perfect shell. They're completely full. They're completely happy. They don't want any more electrons. So the reason they don't appear is because they're happy. They have everything they require. So helium has the highest effective nuclear charge, but it doesn't want, nor can it accommodate, any more electrons. Because remember, here in the n equals 1 shell, you get a 2 and a maximum of 2. So it is fluorine has the absolute highest electronegativity. And where does electronegativity come from? It is this effective nuclear charge in action. Okay, it's the effective nuclear charge in action trying to pull electrons from somewhere else. So n equals 1 is as close as you can get. But n equals 2, do you see we're increasing in protons, but we also have this shielding effect. So n equals 3, n equals 4, n equals 5. It's just going to get worse as we go down. So the generic trend for electronegativity is basically follow the trend to find fluorine. So it increases as you go to the right, and it increases as you go up, and it ends with fluorine. Fluorine is the most electronegative element. Now, I've also color-coded this little picture for you. And what in the world is this? I hope you notice that this doesn't exactly look like the periodic table you're used to, because I have added these numbers in here. Okay, so I still have this atomic weight. But what is this number? That is called the Pauling scale. Okay, the Pauling scale is a numeric value that goes along with electronegativity. Most periodic tables don't have it, and most periodic tables don't need it because you can follow this trend to fluorine. But I put it here because I want to show you the trend in strength. Now, everybody in red, that is the highest electronegativities you can get on the periodic table. They are pulling the most. And so, fluorine is a 4.0. That's the highest you can get. Then, if you will notice, okay, now even though these two are kitty corner, oxygen is 3.5. So oxygen is the second most electronegative element on the periodic table. And then take a look at chlorine and nitrogen. How come they're identical? Remember, if you get into a bigger shell, just because you have more protons doesn't rule everything. So nitrogen and chlorine are pretty much tied at 3.0. So anybody in the red, those are the really electronegative elements on the periodic table. Are you recognizing things? Oh, nitrogen, oxygen, DNA, RNA, all of your proteins. The reason that we can hydrogen bond, okay? Topic for another day, but woo! If you made that connection. Yes. Okay. And then we have the next ones. We have these ones in blue. And those electronegativities are somewhere between 2 and 2.9. So they're still pretty good. And if you'll notice, most of the rest of my non-metals are in this range, somewhere between 2 and 2.9. And I want to point out one special relationship. Okay, one special relationship between carbon and hydrogen. But before I can do that, I have to tell you what is the power behind the Pauling scale. Well, the Pauling scale says that if you have different electronegativities or different poles, if you make a covalent bond, you're not sharing equally. So a polar bond, let's use a different color here. A polar bond does not share equally, so it has different electronegativities. A nonpolar bond shares equally, and so they have the same or identical electronegativities. So if I made diatomic oxygen, this bond is between two oxygens, and both oxygens have the same electronegativity, so this is nonpolar. Where if I put it between oxygen and hydrogen, these are different, and so this one is polar. And the bigger the difference in electronegativity, the more polar it is. Okay, so the larger the difference in electronegativity, the more polar it is. So, whoop. The bigger the difference in electronegativity, the more polar it is. All right, now let me go back to this carbon-hydrogen issue. Now, I'm an organic chemist, so carbon and hydrogen are near and dear to my heart, but in organic chemistry, we usually consider that bond pretty much nonpolar. Okay, so carbon and hydrogen, we pretty much consider it nonpolar. Why? Well, carbon, okay, over here is a 2.5, and hydrogen is a 2.1. So technically that is polar. I mean, technically it's polar, but you see they're so close to each other that it's not very polar, and so a lot of times we just say that the carbon-hydrogen bond is nonpolar, but technically it is. So it kind of depends on what you're talking about, where you're actually applying this knowledge. So if you hear somebody say that that carbon-hydrogen bond is nonpolar, don't freak out. It's so close that to our purposes, it doesn't matter. But when you're doing general chemistry, the answer is polar because they have different electronegativities. All right, so we've got our way to predict our electronegativities. We have kind of this idea between a polar bond and a nonpolar bond. We know why the noble gases are not showing up because they do not want electrons. Yes, they have effective nuclear charge, but they do not want electrons, so we don't consider them with electronegativity. And then there's a few things missing on this periodic table. So, if you will, let's see, different color. Do you see that there's no numbers right here? All right, and then I'm missing the lanthanides and the actinides. Well, some of them, we don't even know what their electronegativities are because they're synthetic and they don't stick around for very long. But the lanthanides and the actinides, well, they pretty much have, 1.1 to 1.8 kind of variation. But when we're dealing with electronegativities, it's usually the non-metals. That's who we usually care about for Lewis structures. So those ones are the most important. Okay. Electronegativity, how much an atom wants electrons or how hard it's pulling towards itself. Fluorine is the absolute most electronegative, and so compare everything to it, and that gives you the generic trend. If you need more specifics, find the Pauling scale, okay, and that will give you the exact numbers. All right, this is like seriously exciting. Hope that helps. Jolly out.